Okay, so this is the problem solving session for the first Cubical Agda sheet, or one of them at least. And yeah, so I hope we can do this a bit interactively. So if you don't mind, you can just unmute yourself and make suggestions. Otherwise, if you feel more comfortable, write in the chat and I'll try to read it out. So it's all recorded properly. Okay, let me share my screen. I hope you can all see my Emacs. I'm going to try to trying to monitor the chat. Okay, so this is the first Cubical Agda sheet. So yeah, we have a different prelude now, but the notation should be almost the same as what you've seen in Martin's and Dan's lectures. So yeah, let's just get to it. Part 1, exercise 1. State and proof FunExt for dependent functions. Maybe we can move to where would it be defined in lecture notes. Okay, Control S is searching in Emacs. Oh yeah, here it is. Okay, so you see we have two functions f and g from a to b, so a and b some types, and then the p that for all x and a we have a path f of x to g of x, and we want a path from f to g. Okay, so what would that look like for dependent functions? Maybe if you want to write your suggestions in the chat. Can you all hear me? No. Okay. Yeah. Okay. There is a good suggestion. Yeah. Exactly. So this is this is just really, instead of going from a to b, it's from x and a to bx, and then the rest of the definition reads out the same. And got a comment in the chat that actually the proof is the same. So we take our h. What is the goal? The path from f to g. Well, so we give it an interval variable I. Wait. Space. Interval variable I. We get some yellow here, but we ignored that. So now you can see this a bit bigger. You can see we have to give it a dependent function. We have to provide a dependent function such that on the boundary, this will just compute to f of x for any x or g of x for any x. So what we can do is we give it one more x. Now it's something of type B of x. Well, what we did with the non-dependent fun x was we take our h, we plug in x. So this will be a path. This will be, we have a path between f of x and g of x, and we need something in here such that on the boundaries this computes to f of x and g of x. Well, we sort of got this, right? We just have to give the interval variable to this path. And like this, happy. And sort of this line reads exactly the same for the non-dependent case. It's just sort of the flip of the interval variable with the x. I think that's kind of cool. Okay, and now function application for dependent functions. Let's try to find it. Prelude should be Control S for search. Up. No. Okay, maybe it's in the 7 nodes. Here it is. Okay, let's copy this. And then we go back with Alt, comma, or meta, comma. Okay. So, yeah. Oh, someone copied it in the chat. Thanks. Sorry, I didn't see it in time. Okay. So first of all, we want this to be a dependent function. So this is going to be x colon a to b of x. And then we have x and y and a, the path between x and y. And then something here. And maybe we call it app D. This is, I think, in yeah. So now the goal, as you can see down there, is but make this a bit smaller. CL. CL. Comma. Okay, so here we have to provide a type, and yeah, there's a hint saying it should be a path P. So maybe if you have suggestions in the chat, now's the time to run type of what should go there. Yeah, I can. Yeah, oh, yeah. There's this is exactly what we want. I'll copy from the chat here. So we want something between f of x and f of y, but they sort of, one lives in B of X and one lives in B of Y. So this is a path over B of, and then P of I, and I guess should be dependent here. Right, as sort of I varies from 0 to 1, P of I varies from X to Y. So this goes from B of X to B of Y. And on the endpoints, this is sort of well typed. That's a good question. The question was, would the following work? No. Short answer is no. And why does this not type check? So if we look at the error message here, sort of this is something of this equality type. So B of X. So yeah, given of course that X equals Y, then B of X has to equal B of Y, right? But what we want here is a family over the interval. And I guess this has to do with the way with the implementation of Cubical Agda, right? This is like path types are like functions out of the interval that sort of match up on the endpoints. So we sort of have more information here. This is sort of a family from the interval into types, but we also know what this family computes to on the endpoints, namely B of X and B of Y. But when we give a path, when we write down a path P, we're only interested in giving the family and then checking that these endpoints sort of belong to the correct type there. So this is sort of about the order in which things are sort of handled in Cubical Agda, because path P is the primitive, sort of the first argument is only the family, and then something on the endpoints that has to compute. And then actually this guy is, is a non-dependent path, and it works similar, but both are sort of like equally primitive, and we're actually, we go to the definition, you see that this is actually defined in terms of a path P in Cubical Agda. So this is the path with the constant family A. And so path P is more primitive, so we shouldn't use app here. We just give it a family. Is that satisfying explanation? Okay, proving this, it actually works the same way as the normal app. So we have to provide it something of type B of P of I. Well, if we take P of I, this is something of A. So we can apply F to it. And we have these two boundary conditions, but this is obviously true that if P of 1 equals computes to X, so F of that is F of X, or for 0, I mean, and similar for 1 and Y. So yeah, that's that. So as you see, the proofs are exactly the same in the dependent case. here we just write a dependent path. Okay. Exercise 3. Well, yeah. This was 2. Now we're going to part 2. Actually, I don't know why I included this. This is nothing cubical really. State and prove that inhabited propositions are contractible. Yeah, maybe you have a suggestion. Their name inhabit. Yeah, exactly. Copy from the chat. Nothing special here. This is an exercise you could have done before. This is nothing special in Cubical Agda. So maybe if we can look at it really quick at the definitions. So this is what you would expect. Of course, type A is a proposition if for x and y, where the for any x and y we have a path between them. And similarly, contractible type is sigma x of A such that for any y, x is equal to y, and set is defined as the path types being propositions. Okay, so we have to give it two things. We have to give it the center of contraction. Well, we don't have much to work with. That's A. And then a function giving the y, we have to produce a path that A equals y. So this will just be our hypothesis that A is a proposition H y. And then, yeah, someone wrote in the chat that, of course, modulo eta rules. This is, of course, just H of A. So H of A is a function that takes in any element and of A and proves that this is gives a path that this is from A to that element. Okay. Yeah. Let's just move on. Exercise 4. And I'm gonna copy the code. It's gonna be more interesting. So we start here, plug in the H. So H sort of can be read as a proof that for any x, E of x is a proposition, and we want to prove this pi type to be a proposition. So again, proposition was any two elements are equal up to path. So we give ourselves two elements. So these will be two dependent functions, f and g. I have to produce a path between those. So again, we take an interval variable. We have to give a dependent function that matches to what we want on the boundaries, namely f and g. So, okay, plug in x. Okay, so if we look at what we can do, we have our dependent functions f, g, x, but we can also plug in x into h. This is a, so we want something of type b of x that matches f of x and g of x on the boundaries. And we have the information that b of x is a proposition, right? So we can give two elements of b of x, or we know two of those, namely f of x and g of x. So we have a path between those. And then we plug in our I. Yeah, so now we have something of b of x, and we have to check that on the boundaries this computes to the right thing. But yeah, it does. H of x tells us that b of x is a proposition, and then we get a path between those two guys at point I. Okay, question about that? No. Okay, I think this is easy enough. Okay. So next minus or h apply. Yeah, I'd say this is also easy enough to prove. So we have our implicit f and g. We have a proof, a path between them. So this is p. And we want to give a function that takes an x and produces a path between the two values, f of x and g of x. So we give ourselves an x. Produce a path between f of x and g of x. So actually, yeah. Someone wrote in the chat concerning this prop pi that we could use fd. Yeah, certainly. I think it's nice though to sort of spell it out how it works with paths and interval variables and see how the things all come together. Yeah, it's a nice exercise. Maybe use what we've proven before to prove these things. Okay, let's get back here. Maybe if someone has a suggestion, like similarly, we could use app or fd, or we do it the direct way. Okay, I'll do it the direct way because exact same function as fun x, someone writes. Yeah, so this would be p. This is just sort of for the programmers, this is just the flip function, right? Yeah, exactly. Yeah, someone's writing that the most generic type of flip must be wild. I don't actually know what the independent type theory, what the most general flip would be. It's a Yes, thank you. I got the order wrong. This is, of course. Oh, wait. No. Yeah. No, this is, of course, X is of type A and I is in the interval. Okay. And now it gets a bit more. So this is a bit trickier now. Okay. So we want to prove this. We got our age. Got to prove, we want to prove that this pi type is a set. And again, so what needs to be a set is that if we have two dependent functions f and g, then the path type is a proposition, right? So if we have P and Q, the path between f and g, then we want to prove that P and Q are equal. Okay. And the hint was use phonics minus to prove that. Maybe you. You have a suggestion? Anyone? Yeah. Yeah. Exactly. The way forward is to just push on. So we give it an interval variable I. The goal becomes a path between f and g such that on the boundaries it becomes p or q. So we can give it one more interval variable j, and we have to give it a dependent function such that something happens on the boundaries. And now we have two interval variables, so there are 4 cases. So it gets a bit more complicated. But okay, we have to give it a dependent function. So an x. Now it's actually more readable. Yeah. So we have to sort of satisfy 4 boundary conditions. And again, we have our hypothesis h of x telling us that b of x is a set. So if we take any 2 elements of b of x and we have 2 of those, f of x and g of x, then we get that this is a proposition. And that means if we give ourselves 2 proofs that f of x and g of x are equal, or 2 paths between those 2 elements, and those we get from fun x minus. So by the way, maybe I should make a comment here. The minus is backslash hat and then the minus or dash. Right. So proof that f of x and g of x are equal, or path between them, and then one more for q. What do we get? U, control U, control U, control C, control dot. Okay. So now we can start plugging in interval variables. I get some sort of path. So we provided an I, we get a path between f of x and g of x. Provided a j, we get something of b of x, and then sort of it might be a bit hard to see that sort of this matches up on the boundaries if we plug in 0, 1 for I and j. But sometimes the best way forward is just to refine and see if Cubical Agda is happy. Okay. This was exercise 5. Exercise 7. So we have an alternative definition for singletons here. And so in the lecture, it sort of was defined with this path going the other way around from a to x. But if we were to reverse this, we can still prove that singletons are contractible. In a bit, because we're about to get to the more interesting stuff, maybe, and the hits. Yeah, that's what we want to prove. We want to prove that this type single prime is contractible. So we have to give it two things: the center of contraction and to prove that everything else is equal to the center of contraction. And maybe it's best to write it out. So the center again, this will be a pair, something in A. Well, what can we give other than A? And a proof that a or path from A to A would basically only one choice we can put in here. It's going to be Reffel. So this is our center. And then we have to prove that everything else is equal. Construct a path to the okay. So we give it a y, where y will be a pair, so we can pattern match on it. First and second, maybe not too informative. Let's call it B and P. So we have to give it a proof that we have to prove this thing. So path, so we give it an interval variable I. Now we have to provide something of the sigma type. So you have to give something of A, and sort of doesn't show the it doesn't show the boundary conditions as nicely now for some reason, but you can still see it here in the constraints. So if I is 1, then it has to be B, and if I is 0, then it has to be A. So yeah, well, what could we put in here? Giving those constraints. So yeah, so we have to use P, but if we want to do P of I, yeah, it tells us that first is not A, so first is B. I don't know why Cubical Agda is so very confusing now with the error messages. So the boundaries don't match up here, but of course we have to go in the other direction with P here, and then it works. Okay, and now we have to give a proof that P of not I or equals to A, or give a path between this element. So yeah, what I would suggest is give another interval variable. Okay. And now I have to give something of type A such that those 4 boundary conditions are satisfied. So whatever we put in at 0, I equals 0. This I. This should be just A. If I equals 1, this should just be P of J. If J equals 1, this should just be A. And if J equals 0, then this should just be P of tilde I, or not I. So there's a hint. Use a suitable combination of connections and the tilde. So maybe you have a yeah, exactly. So we know what P computes to. So this will be P of something. And now we have to give it something in the interval such that, so this will be sort of a combination of I and J using the connectives, like the tilde and the wedge and the V, the join and meet. So if J is 0, then this should be not I. If J is 1, then this should be A, which is P of isn't it P of 1? So someone wrote in the chat that we know that P of I0 computes to A, but the way things are, P goes from B to A, so this is I1. So this is what we know. Yeah. And similarly, P of I0 computes then to B. Yeah, so if we look at the constraints again, if J is I1, then it's A. And This one is very hard to read. I'm sorry. Yeah, this is yeah, exactly. So with this one, this tells us if j equals 1, then the whole thing should go to, because if j equals 1, this is a, and we know that at 1, this is a. So we maybe want something like j v something. And then this is how it is in Cubical Agda. Sometimes you can try to refine more, see what the constraints are. Well, this I guess this helps us. If j equals to 0, then this should just be t of tilde I. But if j is 0, then the v will just be whatever is in here, right? So maybe this will be okay. Fine. Now, yeah, with these things, they can be very finicky, and Cubical Agda is sometimes not very helpful with producing easy to read boundaries or boundary conditions. And sometimes you just end up trying to find the right combination here that sort of works. Okay. Questions about that, maybe? Yeah, exactly. This is ongoing work, and so when I started working with Cubical Agda, these sort of boundary conditions that you get sometimes with the turnstiles, they didn't exist at all. And yeah, it's much better now, and people like Amy, who's also one of the TAs working on making things nicer. Yeah, thank you for that comment. Okay, so now maybe we can do the next exercise. So this is part 3, exercise 8. And this one is about equality in sigma types. And in particular, it tells us that 2 element x and y in the sigma type, so those are pairs, are equal or have a path if and only if there's a path between the first projection and over this path, a dependent path of the second projection. I don't know if Anders mentioned that, but this is sort of a big part of why it's nice to work in Cubical Agda, because maybe you've seen the characterization where you have a transport along this P of this second projection, and then you get a path to the second projection. This is much more annoying to work with. Okay, so let's prove this. So we give ourselves 2 things, a P and a dependent path. Let's call it Q. And we have to give ourselves something in x equals y. So I here get something on the boundary. We have to give it a pair. And this is something type A, such that the following constraints are satisfied. This just becomes first projection of y at 1 and first projection of x at 0. So this should just be P of I. And now something of this dependent, or B of P of I, such that these things hold, but this will just be Q of I. So easy enough. Maybe for the way back, to give it two things. So we give it a p, which is x equals y, and we have to prove that first projection of x equals the first projection of y. How do we do that? Maybe someone can write in the chat. Yeah, exactly. The idea is to use app. So this is really just app of projection 1 of p. So the nice thing is that really Agda, okay, Agda just sort of treats this field variable as a function from the sigma type into the A. Yeah. No, there's some suggestion. Yes. So I'll copy it from the chat. Maybe wait. I'm gonna do something different, and then we're gonna compare. So now we have to give a path p. And yeah, exactly. We could use fd here that we constructed earlier. So if you compare what we got, sort of ignore this stuff, just the last line. This is pretty much what we want, right? You just have to say what P1 is. Well, this is of course P. Right. And an alternative suggestion was, and I'm going to copy this over from the chat. Oh, there's another question that I'll come to in a minute. But this was a proposed solution. So the first is a path that takes lambda I and then sends it to first projection of PQ, and I guess PQ is just P in our setting of I. Well, if you actually look at it, this just is what app does, right? So this is just eta expanding app. And similar, when we looked at app D, we said, oh, this is just the same as app when you actually write it out. So this is also just eta expansion of this. So this term and this term, they actually judgmentally equal. They compute to the same thing in Agda. Nice. Thank you for that remark. And then there was a question. This how come the real library? So I guess that means the Cubical Agda library on GitHub. FunX can be the dependent one, but we need separate for app and app D. Okay, if we go to funxd, so the way functions are defined are they just dependent functions where the second argument stays constant, right? So sort of we can, functions from A to B are just dependent functions into the constant family B. And then sort of this becomes the same because sort of the rest of the definition of funx just reads the same. And equality of sort of functions is just equality of dependent functions, with the second argument being constant. Whereas AppD, okay, actually, yeah. I mean, I wanted to say that this is a path P and the other one is a path type, but the way things are done, if you remember, is that the triple bar is defined as a path P. This sort of depends a bit on there. Maybe you've heard about different cubical type theories. And yeah, some of them, they have like two different notions of a dependent path and path. But what we could do is, of course, we do an app prime here. A to, and then maybe we want this to be C. C. Because then this will just be sort of, if C is the constant function, right? This will just be sending any I to C of those two guys. Right? But this actually then, this is definitionally the same as path type. And this would just be at the yeah. So it does work in Cubical Agda. I don't remember how it is in the library. Are those two things separate? I need to check. But yeah, this was a good question. Might be interesting to see sort of that this really is just the path P, when sort of this is sort of constant and doesn't depend on the I here. Okay. Now we want to, we want to prove that the two round trips sort of yeah, so we have to provide a path like that. And maybe anyone has suggestions? I'm going to give a hint. It's much easier than you might think. Yeah, exactly. It's as easy as it gets. This actually holds by Raffle. And the other direction, so of course P is yeah, this is actually the same, I guess. It's also by Raffle. So yeah, this is sort of one of the main things for Cubical Agda. Very nice. Okay. Part, this is part 3, but it should be part 4, no? This was part 3. Yeah. I'm gonna change this. Okay, are we doing not so well on time? So probably won't have time to solve everything here. So I would maybe, yeah, maybe you can vote which one of those you want to see, 9, 10, or 11 first. But for this we'll have time for sure. Yes, 10. This one is definitely doable. This one is very hard, and I wanted to, yeah, exactly. I mean, this should be more than 3 stars, and yeah, exactly. So the hard part is doing the round trips. Yeah, and you can do it if you assume what is called the groupoid laws. For example, assuming something like Raffle composed with some p equals that p, and yeah, and these kind of things. These things in Cubical Agda you have to prove using these H comps and stuff. I don't, yeah, and fillers. And we're not gonna do this because we only have 2 more lectures. And but what you can do, of course, is sort of prove these as a or use these results as a black box, because you might know how to use them in prove them in HOT using J, right? And then do the proof. Would you should we look at it and see how far we get? Yeah. Okay. Yeah. Okay. People were asking about the Klein bottle, so let's start with that. Yeah, let's get the torus and torus prime. So lectures 7, 9. Torus. There we go. So this is the torus. Maybe I can copy it with the so, and the idea is that we want this to be the line. This is of course not correct. Right. So we have our point P in the torus, and then yeah, okay. I'm doing this very quick, but sort of the idea is that you sort of fold line 1, line 2 to line 2, and then you sort of get a cylinder, and then you move line 1 and line 1 together, and if you want to get the Klein bottle, you sort of add a twist here, right? So you sort of twist things and go in the other direction. So this twist is just okay, and yeah, I'll just give the one definition. The other one uses a composition of paths instead of a path P here. But let's do exercise 10. People seem interested in that. Okay. What's in the chat? Yeah. Should we do the unit first, or should we just jump to the sphere? Is everyone happy with the unit? This is not too hard. Yeah, let's skip. Or this is the other definition of the line bottle. I'll just copy the unit here. Oops, that's not the right one. Okay, so the unit is not too hard. We use either to path. We have two functions to and from. Yeah, and then the functions are straightforward. Sort of, you only have one choice really, and then everything computes by REFL. If you haven't done it, I encourage you to sort of start pattern matching here. Look at the definitions. You'll see you only have one choice, and then when you do the round trips, yeah, you see that you don't have that much choice. No, that everything computes by REFL. So the hard one. Oh yes, that is true, of course. You could have of course add a tilde here, and then if you add a tilde here as well, then everything would still compute to REFL. Otherwise, things get more complicated. But yeah, let's say there's one straightforward choice. Okay, let's do the maps. 2 goes from sus bool. Right, the mode stop working. The 2 mode. One. Two off. Question mark. Okay. Pattern match. Here we can pattern match on A. So the suspension has 2 points, north and south, whereas the sphere only has 1 point, right? So we want to send both of them to base. And now we have 2 paths, meridian at true and meridian at false. And the sphere only has 1. So we want to send one to loop and the other one to ruffle, which then is just at point I, this will just be base. Okay. This is sort of the standard choice. So far, everyone on the same page? Yeah. And then the other direction is from S1 to So here there's less to do. Well, we have to make one choice. Let's say north. Right. Send this guy to north. And then we have to give a path from north to north. We only have paths from north to south though. But can of course compose them. So if we go mirrored true, so we go from north to south, and then we go to south, from south to north. And then of course have to give it the I. Okay, is that what everyone got, hopefully? So this will be now all S in S1. What is it? True of S. S. Okay. Again, we pattern match. Yeah. Okay. Yeah. So yeah, there's of course some. You could of course decide differently on true and false here, and the north and south and so on. Then yeah. Then things will become a bit switched. But okay, if we have to prove that base equals base. Well, I mean we could do loop, but let's just do raffle here. And this is where things get tricky, right? Now this looks scary. But so you might wonder where this thing comes from. I don't know what, yeah. And I mean, Anders didn't want to talk about it too much, and I don't think he'll do it in the next lectures because sort of this is more about homotopy type theory and the way cubical type theory works is you add all these primitives. So you have a very simple notion of what a path is, right? Function out of the interval matching on the endpoints. But in order to be able to do all the things that you're used to doing in homotopy type theory with paths, namely J, and all of that, you sort of have to add extra structure. And this is what these HCOMs are. So in particular, the existence of HCOMs, they just add new terms to a type theory, and they ensure that you sort of can compose paths. Yeah. So this HCOM here comes from this composition here. And maybe we can give it another. Yeah, people were complaining about HCOMs. I see some yeah, some people having suggestions in the chat of how to make sense of this. Yeah, so I'm gonna make it a bit easier. I want a path of paths, and this will be a path between two paths. On the one hand, so this will be something equals loop, right? And I think I'm really going in the same direction as the suggestion in the chat here. I'm just going to rewrite it a bit. Hope you. And this sort of this is gonna be this guy, and sort of if you ignore the HComp, we see a 2 here, and we see a sim-mirrored false here, which comes from this guy. This guy, yeah, and a loop here, which comes from 2 mapping mirrored of true to the loop here. If you ignore everything else, right? So what this actually is, and you have to trust me on this, this is app of 2 to this guy. And now, assuming this, yeah. So again, this guy is this guy. So if you look at it, so we want this to be REFL if I it's any of the boundaries. So if we, but it's like either this side or this side on J. So we give it a J first, right? So if J equals 0, then it's this guy, which is this guy. If J equals 1, then it's the loop. But if I is something, well, this will REFL of J will just be base, of course. Yeah. So we have a flip here. Yeah, this was also in the suggested solution in the chat. And now how do we prove this? And I'm going to use the equality reasoning syntax here that Martin used as well. Okay. So one thing we can do with app And this is like a lot of lemmas going into here, is that it distributes over composition. So in the goal, it says it was this horrible H comp, right? But actually, if you write it like this, you can sort of guess the lemmas. So we can sort of, yeah, we can distribute app over path composition. And actually, this is not a very special lemma. This holds by Raffel, at least in this case. It should, I think, yeah, it should always do that, actually. Yeah. So then the next step is, well, we said we send merit false to base everywhere, so to Raffel. So this will be app of sim of Raffel, sort of. Okay, yeah. What you can do is, yeah, I'm sorry, I haven't merged the pull request with that part of the solutions, and I added that to the I added it to the prelude now when I was writing the exercises, but I didn't quite finish before the session started. So I'm going to do this later, and then you can try to do this for yourself. The next part here is that sort of 2 of merit false of I is always base, right? So app of 2 to this guy, this will just be lambda I mapped to 2 of merit false of tilde I, which will just be base. So this actually is just Raffel. And this also just holds by Raffel. And then one more step is, well, we said true of merit true of I is loop of I, so app to merit true. This is just this is just loop. And again, this holds by Raffel. So the only thing that's needed here is loop composed with Raffel equals loop. And this is a little lemma called R unit that's not yet in the prelude, but it's going to be there. This is going to be R unit of loop. And here, R unit is type for all P. Yeah. Or actually, yeah, it's just any P, right? Yeah, sorry. Okay. So we're gonna leave this whole for now. And okay, there were some questions. So why does the first equality hold by Raffel? You mean this one? Yeah. So this is sort of how yeah. So I don't want to go into details here, but HCOM sort of solutions to sort of square filling problems and no, wait, sorry, yeah, sort of from here to here, right? Yeah. So you have one square and this square happens in suspension of Boole, and this is sort of one path that's sort of the lid of a square. Then you lift the whole square to something in S1, and you'll see that all the other sides of the squares will just be those lifts, and the solution will just be that composition. And yeah, this is sort of because HComp is defined recursively on what kind of function, what kind of type it lives in, the problem, and sort of if it's a function type, then I don't know if that was very helpful. Yeah, this is maybe it's good enough to leave it at that and say this is something that works in Cubical. Yeah, exactly. It's sort of because if you look at the goals, you get some horrible HComp, and you sort of have to see that this is this guy really, and okay. Do you guys want to move on and do the other direction? Yeah, the R unit sort of you can't prove without HComps and H fillers and all these primitives of Cubical that we not going to talk about. So yeah, I'm gonna rewrite the exercises a bit. I should have given a hint. Yeah, I'm sorry. Yeah, very good. If we have time, do you want to look at the the other direction? I was really underestimating the difficulty of this. I'm sorry. I'm going to give more hints. And I found it even harder to reduce it to lemmas that you can just believe maybe and don't use any HComps. So there's a lot of pattern matching going on. This is just referral. This is maybe just mirrored of 2. Doesn't really matter. No, sorry. Pattern match over A. This is the hard direction. This is the hard part. This is a bit easier. Or is it? Did I do something wrong here? Yeah, this wait, it was like I'm a bit confused. Well, does this make a difference? Yeah, okay. Yeah, you have to be clever here. Yeah, you use connections. Give it another one, and then this is J wedge I. So chat. Yeah, very well. So this is already tricky enough, maybe, but this one is quite tricky. Can give it a J, I guess. and then you have 4 boundaries. And yeah, I have to add some stuff to the prelude as well. But the idea is this sort of corresponds to a square where we have this composition here, and I don't know how to explain this without getting into any yeah, exactly. This is a sort of a path P. Yeah. It's called path P helper. I'm trying to, there's some lots of, right? This is the path P. And this is P helper, but also flip now. Yeah. Okay. Now I'm gonna what I want to do is actually I want to have this as a no, I'm not sure if this goes sort of in the right direction. What I want to do is sort of flip this guy. So this will of course complain. This be south. No, right. Have to think a bit. This and then these two change, right? Yeah, no, wait. I want to say this is, yeah, like this. Okay, sorry. This is what I wanted. And if you write this out as a square, then what you get is north here. This will be just the north, because the left side will be REFL. And then here we go to south with this is very true. And here we go to north, which is with this composition. Cool. And here you go with sim arid. Okay. This is sort of this path P, right? As J goes from 0 to 1. So this is the J direction. We go from this guy down to this guy. Yes. No, oh yeah, maybe I should. Yeah, I'm sort of upside down here. Like this. So I don't know if you remember the Anders. No. Did he do? Yeah, in the lecture he should. Yeah, he showed you. I think this is sort of actually just the square 4 composition. This is REFL, and yeah, so this square has a trivial filler, which is also one of the basic lemmas. Yeah, this is a very basic lemma in the library. I don't know if I can add any. Yeah, exactly. If you look at it in the library, you see this square maybe flipped. Yeah, flipped like this. And these squares have fillers. So this path P has a canonical inhabitant. I feel like this is yeah. I don't know if I want. I probably fail. I can. Okay, let me look at the. Yeah, exactly. It's the comp filler. Can we do this? Um, oops. So this will be something called an H-fill. X will of course be north. Q then be merit true. No, similar. Let's see. No, parse error. Yeah. So this standard lemma from the library called compfiller just applied to this case. I'll copy that into the prelude and use it in the solutions and write something about it. Yeah. Yeah, so the question was, if we're not engaging with HCOMs and H-fills, are we really doing cubical GT, or are we just doing hot via a particular interface? Actually, that's what we kind of what Anders is kind of trying to do with his lecture series. Sort of getting intuition for these HCOMs and H-fills in terms of squares like this. I think that's very important if you want to do more cubical type theory and sort of explain why cubical type theory works for doing homotopy type theory. But yeah, for what we want to do, so we can use HCOMs and H-fills to prove the J rule, for example, path induction, and then we can just use that everywhere. And then it's like we're doing things with an interface, and sometimes we want to cheat by doing something sneaky, which we couldn't even write down in HOT. I don't know if that's a good way of thinking, but I think in the next lectures we also will move a bit away from this sort of very fundamental hits to more to different hits like set quotients and stuff, where these things don't pop up as much, and you can sort of use composition and these cancellation lemmas as black boxes, and use it as an interface. Are there any other questions? If you do you want to see the last exercise, or now the last exercise is, I would say, very similar to this one once you guess the right thing. So I'm gonna skip that. Maybe drawing a square for this guy. This is a bit different, difficult actually. Drawing the square for R unit. Well, you can prove it very similarly. if you draw the square for the composition of P with REFL, then you get your point X, say. This will be P composed with REFL. This will be just REFL. This will be P. This will be. So if you sort of interpret it as a path P the same way here, but just flipped, right? So this will be path P from, and then it's, yeah, from, so this will be path in X to Y. And yeah, so basically a similar H filler would work here for our unit. Hope that helps. There were also some questions about literature. Yeah, there's the paper. There's also maybe some sort of better. They don't explain much on how to think about these things in terms of these squares. There's maybe better the categorical explanation. Yes. So what you actually do is you model your type theory in the category of cubical sets, and then these cubical sets have what is called a Kant structure. So this is the composition and the transport, and yeah, these actually correspond to fillers of certain diagrams, which are the squares we have been drawing. Yeah, there's our unit. Yeah, nice. Yeah, good job. Yeah. How is it different from simplicial sets? That's a question for the topologists. But yeah, simplicial sets also have a Kant structure. The way why this is more, or why you see this more in cubical type theory, is that you sort of put this as a structure into your type theory as new, as a new as new primitives to make everything compute and make the theory constructive. Okay, wait, I'm gonna try to find a resource. Yeah. No, but yeah, yes. This is I'm gonna put a link here. This has much more diagrams and sort of explains how to read them if you want to read up on it. I think this is a really nice source, and want to learn how to solve harder squares and HCOMs. I think this is a good starting point if you want to get really into that. stuff. So yeah. I would say that we call it a day for today, but thanks for your time and for your help and good work. Some people were getting really far on these exercises, even though not really solvable with what you've seen. So yeah, keep it up and see you soon. I'm gonna stop sharing and then I'm gonna stop the recording.